Alrighty, so we'll get to this little picture over here in just a minute. What I want to do first is to talk about what we're doing here. We're talking about work done now by non-conservative forces. Friction, air resistance, stuff like that. Okay? The normal force even is a non-conservative force. Okay? Anything that's not a spring force or gravity is going to be a non-conservative force. Okay? And I want to say something about this. I left this up from last video, but I need to say quickly that I wrote this thing, I wrote these three statements, I put them in a bubble, and then I said when only conservative forces do work, but that's misleading. This last statement here is always true. That's just the definition of total energy. Okay? What is true is that only these, let me see, you get a nice bright green one. Only these two are true. I mean, those are the same thing. I've been to that before. Delta E equals 0 is the same as EF equals EI. That is true when only conservative forces do work. Okay? Again, this has got nothing to do with the topic of this video. This is just going back and being clear about what I wrote up here, because it could be misconstrued. This thing here is always true. That's just the definition of total energy. Okay? It's these two things that are only true when conservative forces do work. Now, so let's look at this. Let's say what we've got here is delta E equals 0. Okay? When only conservative forces do work. Now I'm going to erase this. But when non-conservative forces do work, this is no longer true. So this, as I've already said now about 8 times in the last 2 minutes, this is when conservative forces do work. But when non-conservative forces do work, we have to rewrite this way. We have to write this as delta E equals work non-conservative. This is what we have to use when non-conservative forces do work, like friction, or when the normal force does work, or air resistance. We have to use this. Now notice that this, in the case where no non-conservative forces do work, becomes that. If work non-conservative is 0, we're back to our original conservation of energy. But when non-conservative forces do work, energy is no longer conserved. Okay? When non-conservative forces do work, energy is no longer conserved. That is, EF and EI are no longer equal. Okay? This is always true. And it covers those cases when the work done by non-conservative forces is 0. All of the cases we've already done. Right? Let me see. The case of the water slide, the case of the perpetual motion machine, the case of the home run. Those can all be worked by this formula in the box. It's just that the right-hand side is equal to 0. There's no non-conservative work being done. But this is a case, yes, that's the Empire State Building. That's a case we're about to do when the right-hand side is not 0. What we've got, let's explore using this now. What we've got is the Empire State Building, and we're going to drop a quarter. That's a quarter. It's not to scale exactly. That's a quarter falling from the observation deck at 1,250 feet, 381 meters off the sidewalk. We're going to release that, and the quarter is going to fall. And so its initial speed is 0. Its final speed is going to be about 62.2 meters per second, which is about 139 miles per hour. And what we want to know is two things. What is the non-conservative work done? And if we have time, we'll talk about what was the drag force, the force of air resistance. F sub d, drag force. Our displacement is down, obviously. That's our d vector right there. Right? I can. That's d. Actually, I'm going to drop that. I think it's a little confusing. Obviously, it's a vector pointing down. Displacement. Okay. So in order to do this, we're going to use this expression here. But we first need to draw a free body diagram. So let's see. What are the forces? Well, mg downward, right? Gravity is always trusty. And then there's going to be F sub d. The drag force, like kinetic friction, always opposes the motion. The force of air drag always opposes the motion. So if a baseball is going that way, the force of air drag is opposed to that motion. If the baseball reverses direction and goes to the right, air drag is to the left. So if the quarter is falling down, displacement is down, force of drag is up, mg is down. Okay? So that's our free body diagram. The only thing that makes this different from free fall is that we now have a drag force we're looking at. And it's that drag force. This is our non-conservative force acting. Work done by non-conservative forces. We're going to find the work done by the drag force. Okay. All right. So how are we going to do that? Well, we're going to find delta E. If we can find delta E, the left-hand side, we'll be able to determine the right-hand side. Okay, which is what we're being asked for. So we need to find delta E. So EI. What kind of energy do we have initially? We're up here. The coin is being held at rest out above the sidewalk. We're going to call this, as you might have guessed, the sidewalk itself is going to be y equals 0. That's y final. Y initial is going to be 381 meters. So what kind of energy do we have if the quarter is suspended above the sidewalk, 381 meters above? It's not moving, being dropped from rest. There's no springs here. So this is all gravitational potential energy. So EI is mg yi. We could put our numbers in. I don't think I've got my numbers here. I didn't do it that way. But you could find a value for the energy. Okay. EF, okay, is going to be the energy as it hits the ground. What kind of energy is that going to be, class? All kinetic. Because we're at y equals 0, there's going to be no gravitational potential energy because we called the sidewalk y equals 0. So it's all going to be kinetic. But unlike the earlier cases we've dealt with, these two are not equal to each other. If we put in the mass of the coin times g times 381, we're not going to get the same thing if we multiply 1/2 times the mass times the times the final speed. That's, again, I'm messing up with my subscripts. That should be v sub f right there. V sub f. These are not equal. I probably should have, it would have been nice to calculate these. In fact, I think I'm going to calculate these real quick just so you can see the difference. Okay. Let's do the first one here. This will be very fun for you watching your professor stand here with a calculator. 0.00567, right? That's 5.67 times 10 to the third. That's the mass. Times 9.87. I'm sorry, that's not right. 0.00567 times 9.81. That's our G. Times 381. 21.2 joules. That's how much gravitational potential energy we have to start off with. Let's find the final energy. That's going to be 1/2. Let me put the speed in square. I'm going to 62.2 times 62.2 equals that. times the mass times 0.00567 equals that divided by 2. The final energy is 11.0 joules. Look at that. Is that right? Is that what I've got there? Yes. Okay, so we started off with 21.2 joules of energy up here at the top. But when the thing landed, when the coin landed, it only had 11 joules of kinetic energy. In our analogy of the buckets, what's happening here is we're pouring energy out of our potential energy bucket into our kinetic energy bucket, but we're letting a lot of it spill to the floor. In fact, the difference is 10.2 joules. We have allowed 10.2 joules of energy to fall on the floor. It's wasted, it's gone. It cannot be recovered. That's because of air drag. The kinetic energy of the coin has actually gone into speeding up the air molecules. So the energy is still in the universe, we just can't access it anymore. Okay? We have lost energy. So what is the total work here done by non-conservative forces that's equal to the work done by the drag force, right? Because that's the only non-conservative force acting. So W sub D is just the work done by the drag force. Is that going to be positive or negative? Is the work done by the drag force going to be positive or negative? Well, you can find out by subtracting EF minus EI. It'll be negative. It'll be 11.0 minus 21.2. You can also look at the free body diagram and realize that the force is opposed to the displacement. The drag force, F sub D, is opposed to the displacement. And when a force is opposed to the displacement, that force does negative work. So the amount of work done by the non-conservative force is minus 10.2 joules. That is our answer here. Is minus 10.2 joules. So because of air drag, we have spilled 10.2 joules of energy on the floor, and it's gone. We started off with 21.2 joules, now we have 11 joules. The rest of it, gone from our system. Okay, it's still in the universe, but it's not accessible. Okay, now the second question was, what is the force of the average? Really, it's an average because the force changes as the coin speeds up. But what's the average force? Well, you can do that by remembering that the work done by any force, say F sub D, equals F sub D times the displacement times cosine theta. This is the formula I wanted you all to memorize and to know and to become one with, the definition of work. For any force F, the work done by that force is the magnitude of that force times the magnitude of the displacement times cosine theta, where theta is what? It is the angle between that force and that displacement. What is the angle between F sub D, the force in question, and the displacement? 180. So that's this is going to be cosine 180, which is negative 1. So we're trying to solve this for F sub D. That's why I wrote this up here. We can solve this for F sub D because F sub D shows up in the work definition. F sub D is going to be equal to the work done. I should just really call this work done by drag. It's a little confusing. I got too many subscripts floating around. Work done by the drag force equals the drag force. So drag force is going to be work done by the drag force divided by D divided by negative 1. And we know these things. The work done by the drag force is given minus 10.2 joules. We found it already. Divide that by 390 81 meters times -1. Notice you've got two negatives, one on the top, one on the bottom. They cancel. And you're left with the average force on this thing throughout this flight is 0.0268 newtons. Okay. There you go. So the work done by the drag force is just the difference in the initial and final energies. And then we use the definition of work here and solved it for the force. That's how we did it. That's what happens when work is done by a non-conservative force. Another example coming right up, dealing with friction.